Welcome to Ask Prep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is states of matter, real gas and van der Waals equation. It is essential for understanding the real behavior of gases, how they deviate from ideal gas laws, and how we can quantify these deviations. So, let's get started. At the heart of this topic, we need to first understand the basic distinction between ideal gases and real gases. An ideal gas is a hypothetical gas whose behavior perfectly follows the ideal gas laws under all conditions. Ideal gas laws assume that gas molecules have no volume and experience no intermolecular forces. However, real gases do not behave exactly like ideal gases, especially under extreme conditions of temperature and pressure. This is where the concept of real gases comes into play. Real gases deviate from the ideal gas laws due to two main factors: intermolecular forces and the finite volume of gas molecules. At high pressures and low temperatures, these factors become more significant. As the gas particles are pushed closer together, intermolecular forces such as van der Waals forces, attractive or repulsive forces between molecules, start to have a noticeable effect on the gas's behavior. Additionally, the volume occupied by the gas molecules themselves becomes significant when the gas is compressed. These two factors, intermolecular forces and the finite volume of gas molecules, cause the gas to deviate from ideal behavior. To account for these deviations, scientists use the van der Waals equation. The van der Waals equation is an equation of state that describes the behavior of real gases by adjusting the ideal gas law for these factors. Unlike the ideal gas law, which is simple and assumes that gases behave perfectly, the van der Waals equation incorporates the effects of intermolecular forces and the finite volume of gas molecules, providing a more accurate description of real gas behavior. To understand how the van der Waals equation works, let's break it down. The ideal gas law, as we know, is PV is equal to nRT, where P is pressure, V is volume, N is the number of moles, R is the gas constant, and T is temperature. While this law works well under many conditions, it does not take into account the interactions between molecules or the finite volume they occupy. The van der Waals equation adjusts for these two factors. The term AV superscript 2 accounts for the attractive forces between molecules. These attractive forces cause the gas molecules to stick together, reducing the pressure exerted by the gas on the walls of the container. The larger the value of A, the stronger the intermolecular forces in the gas. Gases with significant intermolecular attraction, like hydrogen bonding or van der Waals forces, will have a higher value of A. The term B accounts for the finite volume occupied by gas molecules. Since gas molecules are not point particles, they take up space. The larger the value of B, the larger the volume of the gas molecules. At high pressures, the volume of the molecules becomes more significant, so the term B is subtracted from the total volume to give a more accurate representation of the available volume for gas molecules to move in. These adjustments make the van der Waals equation much more accurate for describing real gases, especially when conditions deviate from ideal. It helps predict the behavior of gases under high pressures, low temperatures, and in conditions where intermolecular forces cannot be ignored. However, it's important to remember that the van der Waals equation still has its limits. It is an approximation that works well for many real gases, but at extremely high pressures or very low temperatures, more advanced models may be needed. Now that we understand the van der Waals equation, let's talk about the practical implications of using this equation to understand the behavior of real gases. The equation allows us to determine how a gas will behave under various conditions. For instance, if you know the values of A and B for a particular gas, and you know the temperature and pressure, you can use the van der Waals equation to calculate the volume the gas will occupy. This can be incredibly useful for predicting the behavior of gases in industrial processes, such as in the manufacture of liquefied gases or in the study of atmospheric conditions. These corrections explain various observed behaviors of real gases. For example, real gases exhibit compressibility factors that differ from unity. At moderate pressures, attractive forces dominate, leading to a compression of the gas beyond what is predicted by the ideal gas law. At extremely high pressures, repulsive forces due to molecular volume become more dominant, causing the gas to occupy more space than an ideal gas would. Another important aspect of real gas behavior is liquefaction. Real gases can condense into liquids under suitable conditions, a phenomenon not predicted by the ideal gas law. This transition is due to the increasing impact of intermolecular forces as temperature decreases. The van der Waals equation helps in predicting the conditions under which a gas will liquefy, making it an essential tool in fields like chemical engineering and thermodynamics. Additionally, by studying the van der Waals equation, we can understand why gases deviate from ideal behavior. Under low temperature and high pressure, the gas molecules are packed closer together, and the intermolecular forces become significant. As a result, the gas behaves less like an ideal gas and more like a liquid. This is why gases can be liquefied under these conditions, and why the van der Waals equation is crucial in understanding the process of liquefaction. In summary, the concept of real gases and the van der Waals equation are essential for understanding how gases behave under different conditions. While the ideal gas law works well for gases under normal conditions, real gases deviate from this ideal behavior, especially when intermolecular forces and the volume of gas molecules become significant. The van der Waals equation provides a more accurate description of these behaviors by adjusting for these factors, making it a powerful tool for studying gases in various situations. Understanding how gases deviate from ideal behavior, how intermolecular forces and the size of gas molecules influence these deviations, and how to apply the van der Waals equation will help you tackle a wide range of questions on gas laws and states of matter. Thank you. We hope this explanation has cleared up any confusion regarding real gases and the van der Waals equation. If you found this video helpful, be sure to like, share, and subscribe to Ask Prep for more detailed lessons on chemistry and other subjects. Keep studying, stay focused, and good luck with your exams.